So now that we've talked about moment of inertia and we understand where moment of inertia comes from, I want to present two questions to you. And they are largely the same question. We're going to do one of them kind of together and the other one I'm going to leave for you. But I have two different situations in which I have masses hung on either side of a massive pulley or a heavy pulley. So these problems would be called a heavy pulley problem or a massive pulley problem. In these problems, the pulley itself has the same mass both on the left problem and the right problem. The left problem, it's a disk of mass 3m. On the right problem, it's a composite object that has a ring of mass m and then two rods spun about their middle, each of mass m. And they're hooked together as spokes in the system. Both pulleys have the same radius, and the same two masses are hung on either side of both pulleys. I'd like us to calculate the acceleration of the system. So how fast does the heavy mass accelerate towards the Earth? We're only going to do one of these at a time, and so let's work this problem first. And since you have done a problem like this many times in the past, I think the first thing I should be able to expect of you guys is that you guys could set up the net force equation for each of those masses. I'll give you a second because it should be in your notes. You guys know how to do things. Which mass moves downwards, the 3m mass or the m mass? Okay, so we can start by recognizing that the 3m mass is experiencing a couple forces. How many forces would it be experiencing? Two, so downwards weight and upwards what? Tension. All right, so yes, we existed 3 months ago and we remember things. Not all of us. It's a little concerning. So similarly on this side, upwards tension, downwards weight. Choose a common direction that you call positive. Then work your net force problem. Come on, folks. I should be able to expect more from you. Well, except for those of you who have this all right. But now that we've been reminded of something we did in this class, the pulley turns, right? Are you guys aware of that? That the pulley's going to spin now? The pulley has inertia, and the only way the pulley can accelerate is if the torque on the pulley is unbalanced, which means the two tensions can't be the same. It is the tension in the string that's acting downwards on the edge of the pulley on both sides. And the only way the pulley can accelerate is if there's an unbalanced torque acting on it. So you're going to have to differentiate the two tensions. They're not the same any longer. In fact, I'm going to say that this is the tension on the left side of the pulley, as is different than the tension on the right side of the pulley. So this will be TL, and this will be TR. We can't treat them the same. TL is greater than TR. It's the only way the pulley can spin this direction. So we no longer have the same two tensions, so you can't cancel them out like a bunch of you did. I mean, it's still going to be true that 3mg minus TL equals 3ma. That's going to be true. And TR minus mg is going to equal ma. That's also going to be true. These are the same functions we set up months ago, except now TR and TL don't cancel out. Put these together, these are two different forces. But that's because the pulley's inertia is also part of the problem. So we need to add the pulley to this question now. So I'll set the two boxes over there for a minute, but let's consider the pulley for a few moments. Now, this first part you're going to think is a throwaway statement. It is not. You should take care of it, file it away for later, and actually consider what's happening. The net force on the pulley is 0. The pulley doesn't go anywhere. But again, don't throw this away. There are 4 forces acting on the pulley. There's an upwards normal force acting on the pulley from the mount. There's the pulley's own weight, 3 mg, acting downwards at its center of mass. And then there's 2 tensions acting downwards. And they all equal 0. Don't throw that away. It's important that you look at this. The normal force here is interesting in that this system has a center of mass that's actually moving downwards. So the net force upwards isn't equal to the net force downwards. The system's accelerating. And it's a common question on the AP exam because the heavier box is moving downwards. But the thing I want you to pay attention to is net torque. It does not equal 0. The pulley's accelerating. This is how the inertia of the pulley gets worked into the system. There are 2 torques acting on the object. There's a torque from the left tension and the torque from the right tension. Now, I'm not going to write a little chart like we did for statics. I'm going to hope you guys are a little more sophisticated and do remember how to calculate torque. And I'll write down here at the bottom, and this is because this is second period. Sometimes I need an extra reminder or two. But torque has 3 parts: the torque arm length, the size of the force, and the angle of between the torque arm and the force. I don't think this part's much of a stretch. The torque arm length will be the radius of the pulley. And the tensions are going to be the forces that are acting at that torque arm. And because this is a pulley, the angle will always be 90 degrees because the string will always come off the pulley at a tangent. So that part we don't have to worry too much about. But we'll get R times TL times the sine of 90. That's got to be the torque that's acting to cause the system to rotate in a counterclockwise direction. That's why I made that one positive. The other one, R times TR sine 90, will be the other torque acting on the right side. It is negative because it's causing a counterclockwise rotation. And this all has to equal I alpha. But I isn't an unknown. This is a disk of radius r and mass 3m. How do you calculate the moment of inertia of a disk? 1/2 mr squared. We proved it yesterday, but it's also on your table of moments of inertia. A disk is worth memorizing. So 1/2, but this disk isn't m, this disk is 3m. Now we can reduce this a little bit, but before we do, I want to point out that in any problem that has rolling or has boxes attached to a pulley, just about any one of these questions, there's going to be a part of your problem where part of your system is going to have an angular component and part of your system is going to have a linear component. You're going to have to bring these things together and figure out whether they're related or not. This usually isn't hard. So I would always ask you to consider a point on the edge of the wheel. Is a point on the edge of the wheel related to the speed of one of your boxes? If it is, then you can probably use A equals alpha times R as a means of bridging these two things together. But don't be complacent here. Be thoughtful here. It's not always going to be true that this will work out. I can give a simple example of where this becomes a little bit more confusing. And let me just show you that example so that you have it someplace in your notes. Consider a stacked pulley. A stacked pulley would be a pulley in which there are 2 different radii of the pulley, like a sprocket or a set of gears. So let's say this is R and this is 3R. If I have a box hung on this side and a box hung on this side, do you realize that these two boxes would have different linear accelerations? The wheel can only have one acceleration, so this thing will accelerate at alpha. But this box, it'll have an acceleration equal to alpha times 3r. And this box will have an acceleration that's going to be equal to alpha times r. So if this does spin, and I don't even know which direction this would spin, but if this does spin, the two boxes won't have the same acceleration. You follow what I mean? That you have to carefully consider what the relationship will be between your linear accelerations and your angular accelerations. It doesn't take much to change them. Now, getting back to our example, I think it's probably pretty reasonable to suggest that this will be true, since the point on the outside edge of our pulley contains our string, and our string is attached to our box. You guys follow along with that? Is that a yes or a no? Okay. So I'm going to make a substitution, and I'm going to reduce this relationship down. First, I'm going to get rid of all the sine 90s. They're just in the way. And I'll get r times TL minus r times TR equals 1/2 times 3m times r squared times a over r. That's a lot. And on your list of steps, when you start talking about forces, and now we've added torques to that, one of the things you're probably going to have to add is, can you bridge your linear and angular variables together? So I'll take a pause here. In your notes, write something to yourself about why we use this and how. My choice was to put everything in terms of the linear coordinate, because we were asked for the linear acceleration of the box. Now, listen up, you mathletes. You guys who know things, if you're looking carefully at this, can you see that we can do some reduction here with the r's? I have an r squared right here, so I can get rid of the r squared and cancel it with that r. You guys see that okay? Do you also see that there's an r still left in every term of the problem? So we can factor that out and get rid of it. Do you see that okay, or do I need to be more explicit? We all okay with that? You said yes, so that's good. That means this becomes TL minus TR equals 3/2 MA. All the r's have disappeared. Now, not wanting to distract you too much, if we look now at what we've generated three relationships. This is the pulley. This is the box of mass m, and this is the box of mass 3m. These are the reduced relationships that discuss the acceleration of each of those things, linked by the same acceleration. So this is the linear acceleration at the edge of the pulley. This is the physical acceleration of each box. If you've done this correctly, you should be able to add these together just like we did before. And if you look closely, I have positive TL and negative TL. And I have positive TR and negative TR. Do you see that? If you've done this correctly, your internal forces should cancel out, just like they did when we did this way back in October, even though we're including the pulley. So if I add them all together, I'm left with 3mg minus mg on the left side. All of those terms on the right side have an a in them, but I have 3 halves m plus 3m all times a. Now this should look real familiar to you from first semester. This side is the net force part. We still hung just 2 boxes on our system. They are what's causing the system to accelerate. They represent the unbalanced forces acting on the system. But now we have 3 things included here. Anything with inertia shows up here. And this is the 3m box. This is the box of mass m. This is the pulley's inertia. This represents how the inertia of the system affects how the system accelerates. So just like before, you're going to add that stuff together. I'll get 2 mg on the left side. And let's see, 3 halves plus 2 halves plus 6 halves. It looks like 11 halves ma. If I want the acceleration of the system, you just solve this for a. I'll cancel the m's out. It looks like 4/11 g equals a. The problem is generally done the exact same way we did it first semester. A net force equation for each object in your system. And anything that's spinning, a net torque equation. You try. Before you try, let's talk about the difference between this object and what we just did. This isn't a single object, it's a composite of 3 objects. So our moment of inertia here will be the moment of inertia of the ring plus the moment of inertia of a spoke plus the moment of inertia of the other spoke. Right, 2 spokes in a ring. You're going to have to add these things together because moments of inertia add together. So the ring is simple. The moment of inertia of a ring about its center is just mr squared. What's the moment of inertia of a rod about its center? Go ahead. Yeah. 1/12 ml squared. So L is the length of the spoke. So I have to put 2r here for the length of the spoke, right? Because the spokes are a diameter long. And there are 2 of them. Now, 2 squared is 4. 4 times 1/12 is 1/3. Does that make sense? So I have a third plus 3/3. So this all comes to 5/3 mr squared. Before you launch the problem, you guys who are just writing things down blindly because you're not able to think this fast, maybe take a few seconds and write yourself a note about what we just did. We had a composite object, so we had to add up the individual moments of inertia to get the moment of inertia of the object. I'll wait patiently while you give yourself some information there, so that when you see it tomorrow, it'll make sense. This is the exact same problem now, just a different moment of inertia. Repeat. Give yourself notes. Use the notes you had. Come up with an answer. I'm looking for the acceleration of one of the boxes. I'll come by and check your work. 6/17 g. It's largely the same as the other problem, so we're still going to have something like 3 mg minus tension on the left equals 3 ma. That's still going to be true. And tension on the right minus mg is going to equal ma. That's still going to be true. What differs isn't even those torques. The torque is still going to be RTL minus RTR equals, this part's different. The inertia of just the ring itself, which is 5/3 mr squared. That's the inertia of our rod and spoke combination. Times alpha, but again, I think we can replace alpha with a over r to put this all in terms of the linear acceleration. Now this reduces down immediately to TL minus TR equals 5/3 MA. And now you proceed from there with the same algebra. And yep, you do your algebra correctly, 6/17 G. Now, not particularly tough, but you can probably see that every time we had a pulley first semester, your pulleys can have inertia, and they can be of any number of shapes and sizes. This isn't the only place we're going to use this, but this is the start. I do have a few other things I want you to consider, though. Ways we can put these problems together that maybe you haven't thought about. So I'm going to move on to another page. Are we good for that? First, I talked about the stacked pulley a minute ago, but how about something like this? What if I have two wheels that touch at a single point, and there's enough friction where the two wheels stay with a point of contact? If I start to spin this wheel this direction, is it clear that that's going to cause this wheel to spin in this direction? Does that make perfect sense? All right. Is it also clear that the big wheel has a bigger radius than the yellow wheel? Well, this is important because this point is considered a collinear point in that that point will have the same linear speed for both wheels. If it moves without slipping, that point has to have the same delta x, v, and a has to be the same for that point. But that means that this wheel on the right, the blue wheel, will have its own variables here. That will be different than the ones for the yellow wheel because the two radii are different. So although the point in the middle has the same linear speed or the same linear acceleration, they have different angular accelerations. This is how gears work. Gears of your car constantly swapping in a different sized wheel all the time in order to change the ratio between how fast the engine is spinning and how fast the drive shaft is spinning. That's how your automobile works. Most of your cars are front-wheel drive, so it goes right to the wheels from there. Some of you have what's called a continuously variable transmission, where this thing is more like a cone that slides backwards and forwards to continuously vary the gear ratio. But this is how gears work. It's not that dissimilar from, say, a bicycle, which does the same thing, but by adding the addition of a chain to lock these things together. Right? Still going to have a collinear portion because the outside part of the chain is collinear to both wheels, but the two wheels have different angular properties. One rotation of the big wheel is many rotations of the little wheel. And if it is a bicycle, then you get to add even more fun because that means there's another wheel connected to the gear. These two are coangular in that the angular speed of the gear at the center will be the same angular speed as the wheel on the outside. But obviously the wheel on the outside travels a lot farther than the wheel on the inside. You put that on the ground, and now you have yet another angular to linear combination. And again, I'm not trying to say that you should be prepared for this problem. I'm trying to say this is how mechanical advantage works, by manipulating gear ratios and sharing collinear and coangular properties. We didn't even talk about the fact that in addition to this, there is also the pedal, which is mounted on a torque rod out here, so you put your foot on it to gain leverage over the whole system. Right, this is how it all works. Again, your car is not much different than this. Now, if you have an electric car, it is different than this because an electric car doesn't have gear ratios. Electric cars just apply their power directly to the wheels. But almost everything else in your life probably has some sort of gearing system. pop open the blender or a food processor or even the thing that spins the microwave plate in your microwave. There's going to be a set of gear ratios all over the place whenever you're talking about spinning something or turning something. Now, the last thing about today, in the closing few minutes, is I want to talk about the parallel axis theorem. I want you to imagine that we have a sphere, and a sphere has a moment of inertia of 2/5 mr squared if it's a solid sphere. Okay? I did this a little different in first period, and it didn't really work, so I want to do something in this period that I think might work. I want you to find the moment of inertia of this sphere if we're going to spin it about its center, assuming the mass is, say, 10 kilograms, and the radius is something manageable like 0.25 meters. So it's a relatively big sphere with a diameter about this size. Okay? Find the moment of inertia of that system, please. We need a number here, so... So do we get 0.25? Is that right? So 0.25, and that's kilogram meter squared, the unit of moment of inertia. It's kind of an odd unit, but remember, it's emphasizing the fact that it's about how big the object is, not necessarily what its mass is. Okay? Now, what if we were to rotate it about a point on its edge like this? Okay, so we're kind of swinging the ball around. Does that make sense? We would have to use what's called the parallel axis theorem. The parallel axis allows us to shift to a new moment of inertia by taking the original moment of inertia around the center of mass and adding a shift distance. In this case, x is the shift distance. Everybody follow along with what we're doing here? Now, in this case, we're shifting it one radius, right? We're going from the center to the edge. So can you take a moment and calculate the moment of inertia now? We know the center of mass one is 0.25. But we're going to add to it the shift distance. What do we got now? Okay. Now, do you notice that the moment of inertia got a lot bigger? Simply by moving the axis of rotation to the edge, we suddenly have almost 4 times the amount of inertia that we had before. Do you guys see it? Now this next part is challenging for students. What if instead we were to affix it to the end of a rod and shift it 1 meter away? So we take this sphere, put it on the end of a meter stick, and kind of spin it around in a circle. So this is going to be our new axis of rotation. Assume the rod is very light compared to the sphere. What will be our new moment of inertia now? Now, before you actually get me a number, I want you to look at something, please. the sphere is 2/5 mr squared. But we are shifting it by a distance of 1 squared. Right? We're shifting it 1 meter. Is it clear to you that this is going to dominate the terms here? That it's way bigger than what this is? Yeah. I said to assume the rod is light compared to the sphere. I'm trying to focus on what's happening to the sphere as we move the moment of inertia, as we move the axis of rotation. This isn't a hard and fast rule, but if you're not sure what I'm getting at, I will remind you what the point mass moment of inertia calculation was. Do you remember that when we first started this? You notice that mx squared is the point mass moment of inertia. Do you see that pretty clearly? Once you shift an axis of rotation to a point outside the body of the object, it becomes a point mass. Once you shift the axis of rotation to a place outside the body of an object, its moment of inertia is dominated by the point mass formula. Yes, this still exists, but this is so much bigger. I mean, right now, this is going to be 0.25, and this is going to be 10. That 0.25 barely registers any inertia because it's no longer about the shape of the object. The moment the axis of rotation gets outside of the body of the object, the shape of the object no longer matters, and it becomes a point mass. Now, it's not going to be obvious when you have to do this, but it is common for them to say, okay, I have a rod with 2 spheres on it, and they tell you the mass of the spheres, but don't tell you the radius of the spheres. They just say it's a 5 kilogram sphere, a 5 kilogram sphere, and a 10 kilogram rod of length 1 meter. If we're going to spin this about its center, what's the moment of inertia of the system? And they're going to say, well, how big are the spheres? And what I'm telling you is that doesn't matter. All you need is the mass of the spheres because we're rotating them outside of their body. Right? The axis of rotation is here. Suddenly, their shape doesn't matter. So if they don't give you the physical size of the sphere and only its mass, they are telling you to treat it like a point mass. That's what they're telling you. They're saying that no longer does the shape matter because the object's being rotated far enough away from the center of the object to where its own shape isn't contributing to the moment of inertia, just its mass being away from the axis of rotation is. So whenever you start to rotate something outside of the object's body, you can calculate its moment of inertia by just using the point mass formula, where in this case, R represents half a meter. Now again, this is not a hard and fast rule. If they give you the size of the sphere, you probably should use it.